In the name of God, the most merciful, may the peace be upon you and God's mercy and blessings. We will solve Prof problem 7-38, which is about developing load function W of x, shear function V of x, and moment function M of x by using the discontinuity function. The same problem is P7-62 in the third edition. The Prof problem is included in Professor Timothy Philpot's book, An Integrated Learning System, Mechanics of Materials. We have a given beam. We have a given simply supported beam with a span of 20 feet, acted upon by one downward concentrated load of 3,000 pounds at x equal 5 feet from the left support, and at the same point there is one concentrated moment of 8,000 pound-foot acting anti-clockwise. There is also a limited width downward uniform load of 800 pounds per foot with a length of 7 feet, starting from x equals 9 feet. This problem covers cases number 1, 2, and 5 from the discontinuity table. It is required in Part A to use the discontinuity function to write the expression for load W of x in Part A and to include the beam reaction in the expression. In Part B, it is required to integrate Wx twice to determine V of x and M of x, while in Part C, it is needed to use V of x and M of x to plot shear force and bending moment diagrams. First, we draw the free body diagram for the beam, which includes two reaction forces AX and AY at support A, and one upward reaction force EY at support E, which is a roller support. The total value of the uniform load is 800 multiplied by 7 is 5,600 pounds. Here is the free body diagram. We have here AX and AY, and on the other support we have a vertical load EY. This is a concentrated downward load of 3,000 pounds, and this is the concentrated moment of 8,000 pound-feet, which is acting anti-clockwise, and this is a total load of the uniform load as shown. We have the positive direction as from left to right for horizontal forces is considered positive, from down up is considered positive direction for the vertical loads, while for the anti-clockwise direction for moments, this is considered as the positive direction. We start with the sum of x equal to 0. If we investigate the beam, we cannot find any horizontal forces acting, so we could say that A sub x equal to 0. From the sigma y equal to 0, we can assume that AY plus EY equals 3,000 pounds plus 5,600 pounds. Then the AY and EY will be equal to 3,000 plus 5,600 equals 8,600 pounds. The last equation of equilibrium is the sum of M at E equals 0 for all the forces, considering the anti-clockwise direction is positive. So the AY multiplied by its arm will create a clockwise direction moment, so we consider it as negative. So we say minus AY multiplied by 20 feet plus, this is anti-clockwise direction, 8,000 pound-foot, plus also the 3,000 downward load acting at E with arm length of 15. so plus 3,000 by 15, and the concentrated load 5,600 multiplied by its arm, which is 3.5 plus 4, 7.5, all equals 0. We move the minus 20 AY to the other direction to be positive, and we sum all the other values, 8,000 plus 45,000 plus 42,000, all to be divided by 20 to get the AY value. The AY value is positive 4,750 pounds, which means that the assumed direction is correct, coming upward. From sigma y equal to 0, we have A sub y, and E sub y equals 8,600 pounds. So we could say that E sub y equals 8,600 pounds minus 4,750 equals 3,850 pounds. This is our starting for to get the values of the reactions at supports A and support E. We will move to the next slide. In this practice problem, we have 3 cases, which are cases 1, 2, and 5 in the discontinuity function tables. Case 1 is the case of concentrated moment, which we have anticlockwise of 8,000 pound-foot. Case number 2 is the concentrated load, which includes the reactions at A, the concentrated load acting after 5 feet, and the other reaction at E. While case 5 is the partially loaded uniform load, we have partially loaded uniform load acting after 9 feet from the left support and with limited width, which is 7 feet. We have several regions. We have one region from 0 to 5 feet, followed by another region from 5 feet to 9 feet, then from 9 to 16, and later 16 foot to 20 foot. We start to write the load intensity W of X equals, the first reaction is 4,750 pounds acting upward in the positive direction. So we'll write 4,750 multiplied by, this is Macaulay's expression, bracketed x minus 0 raised to the power of minus 1, and then this is downward load minus 3,000 pounds multiplied by x minus 5 raised to the power of minus 1. Minus, because this is acting anticlockwise, minus 8,000 multiplied by x minus 5 raised to the power of minus 2, minus 800. And we'll stop here. Since this uniform distributed load is localized for a span of 7 feet, we extend to the end. Then we will add an upward uniform load acting for the last 4 foot width. If we deduct the upward load with the downward load for the same span of 4 feet, we will come back to the original uniformly loaded, localized for 7 feet. For the extended load, we write minus 800 multiplied by x minus 9 raised to the power of 0 plus 800 coming upward multiplied by x minus 16 raised to the power of 0, and finally the reaction of the rate support, which is 3,850 multiplied by x minus 20 raised to the power of minus 1. This will be ignored in the calculation since this will start to work for spans more than 20 feet, while we have the beam span is only 20 feet. Integrate one time, so we have v of x equal 4,750 multiplied by x minus 0 raised to the power of minus 1 plus 1, which is 0, minus 3,000 multiplied by x minus 5 raised to the power of 0, minus 8,000 multiplied by x minus 5 raised to the power of minus 1, minus 800 multiplied by x minus 9 raised to the power of 0. We'll add 1, it will be x minus 9 raised to the power of 1, plus 800 multiplied by x minus 16 raised to the power of 1, plus 3,850 multiplied by x minus 20 raised to the power of 0, which is ignored in the calculation. In the next slide, we continue to integrate. We have the expression of m of x equals 4,750 multiplied by x minus 0 raised to the power of 1, minus 3,000 multiplied by x minus 5 raised to the power of 1, minus 8,000 multiplied by x minus 5 raised to the power of 0, minus 800 over 2 multiplied by x minus 9 raised to the power of 2, plus 800 divided by 2 multiplied by x minus 16 raised to the power of 2, plus 3,850 multiplied by x minus 20 raised to the power of 1. Thus, we have completed parts A and B. For part A, it is use the discontinuity functions to write the expression for W of x, include the beam reactions in this expression, and while part B is integrate Wx twice to determine the V of x and M of x. The third part, which is part C, will include use V of x and M of x to plot the shear force and bending moment diagram. We'll start to do this in the next slide. In the next slide, we'll introduce the expression of V of x, and we start to get the values of the shear at various points. This is the expression for V of x. We start by V of x equal to 0. We consider it as 0 plus or small amount more than 0. So we have the V of x equal to 0 plus will be 4,750 multiplied by positive value raised to the power of 1. We consider it 1, while the other items are acting after span of 5 feet. So we consider them as 0 since they will become a negative value, and negative value will be considered 0. So V of x equal to 0 will be equal to 4,750 pounds. For V of x equal to 3, the first term will be 4,750 multiplied by 3 raised to the power of 0 equals 1. So we have again 4,750 pounds. While for V of x equal to 5, it would be 4,750 multiplied by 5 raised to the power of 0 equal 4,750 pounds. We consider what is called V of x equals 5 plus or a small amount more than 5 to express the step function. We have V of x equal to 5 plus will be 4,750 multiplied by 5 raised to the power of 0 minus 3,000 multiplied by x minus 5 will be considered positive value raised to the power of 0 equals 1. So the V of x equal to 5 plus will be 4,750 minus 3,000 equal 1,750 pounds. We will ignore the item of the expression for the concentrated moment since it has no effect on the shear. This was for the location from 0 to 5. What we start to get the values for points from 5 feet to 9 feet. For Vx equal to 7, we have 4,750 multiplied by 7 raised to the power of 0 equals 4,750 minus 3,000 by 2 raised to the power of 0 equal 1,750 pounds. While for V of x equal to 9 foot, it will be 4,750 multiplied by 9 raised to the power of 0 minus 3,000 multiplied by 4 raised to the power of 0. It will be equal 1,750 pounds. For the region from 9 to 16, we start by Vx equal to 10. It will be 4,750 multiplied by 10 raised to the power of 0 minus 3,000 multiplied by 5 raised to the power of 0. We will include this fourth item, minus 80 multiplied by 1 raised to the power of 1. So we have 1,750 minus 800 equals 950 pounds. For V equals to X of 11 feet, we have 4,750 multiplied by 1 minus 3,000 multiplied by 6 raised to the power of 0 minus 800 multiplied by 2 raised to the power of 1 equals 150 pounds. We will notice that there is a drop of 800 bare foot minus 800. We are interested of the point of maximum moment or zero shear. We assume that this point will occur between 9 and 16. So we will write Vx equal 0 will be 4,750. We multiply by 1 minus 3,000 multiplied by 1 minus 800 by x minus 9. This is raised to the power of 1. We equate these three items to 0. So we take this item, we move to the other end, to the right side. So we have 800 multiplied by x minus 9 equals 4,750 minus 3,000, which will give 1,750. We adjust the term and get the value of x maximum. It will be 11.1875 feet. This x is bigger than 9 but smaller than 16 feet. We move to the next slide, and we want to get the values from x equal to 12 to x equals to 20. This is expression again of v of x. For v of x equal to 12, we have 4,750 multiplied by 12 raised to the power of 0, minus 3,000 multiplied by 7 raised to the power of 0, minus 800 multiplied by 3 raised to the power of 1. This item will not be considered because we have x equal to 12. We will sum all these values. We get minus 650 pounds. For v of x equal to 15, we have 4,750 multiplied by 15 raised to the power of 0, minus 3,000 multiplied by 10 to the power of 0, minus 800 multiplied by 6 raised to the power of 1 equals minus 3,050 pounds. For v of x equal to 16 feet, we have 4,750 multiplied by 1 minus 3,000 multiplied by 1 minus 800 multiplied by 7 raised to the power of 1 will be equal to minus 3,850. We have completed 4 places from x equal from 12 feet to x equal to 16. We start from 16 to 20. We take one point at x equal to 18 feet. We have 4,750 by 1 minus 3,000 multiplied by 1 minus 800 multiplied by 9 raised to the power of 1 plus 800. This term will start to work. 800 multiplied by 2 raised to the power of 1. So we have v of x equal to 18 equals minus 3,850 pounds. For the last point at the end, we have Vx of equal to 20 will be 4,750 multiplied by 1 minus 3,000 multiplied by 1 minus 800 multiplied by 11 plus 800 multiplied by 4 raised to the power of 1. It will be summed, all these terms will be minus 3,850 pounds. This is exactly the numerical value of the reaction at support E, which we have already calculated at the beginning. In the next slide, we want to get the expression or the values for the moment at several points starting from 0 until x equal to 11. And this is expression for the m of x, which we have obtained by integration. We start by x equal to 0. We have 4,750 multiplied by 0 equals 0. There is no moment at the left support. While for x equal to 3, we have the moment value will be equal to 4,750 multiplied by 3, which is 14,250 pounds-foot. For m of x equal to 5, its value will be 4,750 by 5. It will be 23,750 pounds. If we get the 5 plus, we consider this term, which is 23,750, and we go to the third item, which is minus 8,000 multiplied by a positive value raised to the power of 0. We consider it as 1. So we will subtract 8,000. The total value will be 15,750 pound-foot. This is the point of application of the anticlockwise moment. It will cause a drop from 23,750 pound-foot to 15,750 pound-foot. Then we start to get the moment values for locations from 5 to 9. M of x equal to 7 will be 4,750 by 7 minus 3,000 multiplied by 2 minus 8,000 multiplied by 2 raised to the power of 0. The final value of the moment will be 19,250 pound-foot. For m of x equal to 9, it will be 4,750 by 9 minus 3,000 by 4 minus 8,000 by 4 raised to the power of 0. It will be 22,750 pound-foot. For m of x equal to 11 will be equal to 4,750 by 11 minus 3,000 by 6 minus 8,000 multiplied by 1. This term will be 1 minus 800 divided by 2 multiplied by 2 raised to the power of 2. It will be 24,650 pound-foot. In the next slide, we continue to estimate the moment value for the points from x 12 feet to x 20 feet. The first region was from 0 to 5, second region from 5 to 9, and then we start from 9 to 16. For the moment at x equal to 12 will be equal to 4,750 multiplied by 12 minus 3,000 multiplied by 7 minus 8,000 multiplied by 7 raised to the power of 0 minus 400 multiplied by 3 raised to the power of 2. This term will be 0 because this will start to act for the values of x more than 16. The final value will be 24,400 pound-foot. For point x equal to 14, the moment value will be 4,750 by 14 minus 3,000 by 9 minus 8,000 multiplied by 9 raised to the power of 0 minus 400 multiplied by 5 raised to the power of 2 equals 21,500 pound-foot. For x equal to 16, the moment value will be equal 4,750 by 16 minus 3,000 by 11 minus 8,000 multiplied by 11 to the power of 0 minus 400 multiplied by 7 raised to the power of 2. This term is still 0 because this value will be 0. So the final value of the moment at x equal to 16 will be 15,400 pound-foot. All values so far is positive. It will continue to be positive. The moment value at x equal to 18 foot will be equal to 4,750 by 18 minus 3,000 by 13 minus 8,000 multiplied by 13 to the power of 0 minus 400 multiplied by 9 raised to the power of 2 plus 400, this term will appear, plus 400 multiplied by 2 raised to the power of 2. We have 7,700 pound-foot. Finally, the moment at x equal to 20, if we sum all these values, will be equal to 0. That is normal because we have a hinge shear, and the sum of the moments at the right support will be equal to 0. In the next slide, we want to get the values by using the Excel sheet. This is the Excel sheet I have used. The sum of AY plus EY equals to 8,600 pounds, which are the 3,000 plus 800 multiplied by 7. Then the AY, this is a value I get by taking the moment, which already matches with the calculation at the first slide, 4,750, and this is the EY. By using the sum, we get 3,850, and this is again another check to get the EY by taking the moment to the left support. That will give us again the same number, 3,850. These are the regions from 0 to 5, from 5 to 9, from 9 to 16, and from 16 to 20. This is starting for the 3 columns. The distance in x for x by foot, and this is the shear V of x in pound, and the third column expresses the value of the moment pound inch. We have a drop here at x equal to 5. We have a drop since we have a shear drop, and also for the moment we have a change in the moment. Also again, there is a change in the slope at x equal 9. Here we don't have any distributed load, and after x equal to 9 we have slope in the shear by 800 pound per foot. How we express at point 5 the value of the shear and the value of the moment. This is the expression that matches with the expression for shear and the moment, except that we use the for 5 and for 5 plus. I put two values for 5 here and 5 here, and in the expression the C19 is the value of the shear at x equal to 5. This is the if and command else. We have A19 bigger than or equal 0, comma A19 less than or equal 5. It is essential to put the equal sign here and less than 5. The shear value here will be only from here to here. The shear value will be equal to 4,750 plus. If we move to from 5 to 9, we will consider that for A19, this is the A19, this X5, for A19 bigger than 5 and A19 less or bigger than 9, we have the 4,750 minus the 3,000. This is the value of the shear. We get the other region from 9 to 16. For A19 bigger than 9 and less than or equal to 16. We have 4,750 minus the 3,000. Then start to act the 800 multiplied by the x value. The x value, the difference of x, is nothing but A19 minus 9, shifted by 9. The expression from bigger than 16 and less than 20, we have 4,750 the reaction, minus the other concentrated load, minus the part of the uniformly distributed load, which is minus 800 A19 minus 9, plus the 800 A19 minus 16. You remember that we have extended the uniform load and then subtract the upward load. This is here the expression. This expression will give us the value of the shear at 5, which will be 4,750. If we want to get the expression of the other point 5, or the drop 5 plus, we remove the equal sign from the first term. We let it A20 less than 5, and we move and we put the expression of A20 bigger than or equal 5. When we apply in the expression, it is the same, but the only difference that we remove the equal sign from less than 5, and we put it here for the bigger than to express the drop. We'll find that the value of the shear will be 1,750 with a drop of 3,000. We still in the shear value. In the next slide, we want to get the expression of x equal to 9. For x equal to 9, we put the value of A24. This is a cell. A24 represents the x value. The x value here will be equal to 9. So the same expression for shear, we put A24 less than or equal to 9. And this is the same previous expression for shear. We get the value of 1,750. This is the cell C24, which expresses the value of the shear for x equal to 9. For the shear value diagram, we have already used the Excel sheet to get the values of x and the corresponding value of the shear, and we use the graph of Excel to draw the shear diagram. The x-axis represents the point distances in feet, while the v-axis represents the shear values for different points. Above the datum will be considered for the positive values, while below the datum represents the shear values with negative sign. We have 4,750, the value of shear from 0 to x equal to 5. Then due to the concentrated load, we have a drop of 3,000 pounds. So we have 4,750 minus 3,000 will be 1,750. Then come the uniformly distributed load of 800 going downwards. So we have a slope or drop of 800 pounds per feet. This is the value at x equal to 9 feet. We have 1,750 going down with a slope of 800 pounds per feet. So in order to get the point where the shear equals to 0, we can divide 1,750 divided by 800. We get 2.1875. Since this value at x equal to 9, we add to 9, we get 11.1875 feet. This is the distance of the point of 0 shear from the 0 axis. If we continue to drop, we have here 7 feet. So at x equal to 16, we have 1,750 minus 800 multiplied by 7. This is the drop. We have 1,750 minus 5,600 equal minus 3 3,850 pounds. This is the value of x, of the shear at x equal to 16. Since the uniformly distributed load will not continue, so the same slope will be maintained until the end. This is the value of x equal to 20, which the value of the shear will be minus 3,850, then numerically equal to the reaction at point E. In the next slide, we want to get the expression of m of x by using Excel. These are the regions from 0 to 5, and from 5 to 9, and from 9 to 16, and from 16 to 20. We have drop at x equal to 5 due to the concentrated moment of the anticlockwise by value of 8,000 pounds per foot. If we have a look to the attached Excel sheet, we have 3 columns A, B, and C. This represents the shear value, which we have already talked about, while for the column of C, this contains the values of the moment for the various distances of x. For instance, if we have for the region of from 5 to 9, I put again 2, 5. For the upper 5, the value is 23,750, and how we get the expression? If we check the expression of if and, we have this A19 expresses the x expression. If and we have A19 equals or bigger than 0, comma A19 less than or equal 5, we put the equal sign here. What is the moment value? The moment value is the reaction multiplied by the distance. The reaction is 4,750 by A19. A19, again, this is the x distance, comma, if and, this is the start of the other region from x bigger than 5 and less than 9. So A19 bigger than 5 and A19 less than or equal to 9 equals 4,750 by A19 minus the 3,000 multiplied by A19 minus 5. This is a concentrated load moment R. A19 minus 5. Minus 8,000, this is the moment, multiplied by 1. For the other region, for bigger than 9 and less than 16 or equal 16, we have 3 items, 4,750, the reaction moment, minus the 3,000, A19 minus 5, this is the moment due to the concentrated load of 3,000. Again, minus 8,000, but at bigger than 9, it will start to appear the uniformly distributed moment of minus 800 due to the uniformly distributed load. The moment of the uniformly distributed load will be 800 multiplied by x minus 9 multiplied by 1/2. This A19 or x minus 9 raised to the power of 2. For the x or A19 bigger than 16, less or equal than 20, we are here. From 16 to 20, we have moment from the concentrated load, moment from the reaction load, then moment from the 3,000, moment from the concentrated moment, and moment due to uniform load. You remember that we have extended the negative and we used an upward uniform load of positive sign. This will be expressed in that expression, 4,750 multiplied by A19 minus 3,000 by A19 minus 5 minus 8,000 multiplied by 1 minus 800 by x or A19 minus 9 plus, this is a uniformly distributed with 800 plus 800 multiplied by x minus 16 by 0.5. This A19 minus 16 is raised to the power of 2. This is a moment due to uniformly distributed load, comma, 0. So for point 5, the upper point 5, we use the expression of minus 5 and equal 5 to get the value at 5. While for C20, C20 represents the moment at x bigger than or equal 5. We remove the equal sign from less than 5, and we put it here, but it will be A20. The x value for the second point will be A20. We use bigger than or equal to 5 to get the value of the moment after the concentrated moment has been applied. And this, the value will appear at cell C20. This is the C20 cell. This is the bending moment diagram drawn by using the Excel sheet based on the tables A, B, and C. We started the moment at 0, then we move until x equal to 5. At x equal to 5, we have 23,750 pounds. Then comes the drop at x equal to 5 due to the anticlockwise concentrated moment, the drop of 8,000 pound-foot. So we have a value of 15,750 pound-foot. Starting from this point, we have slope until we get, this is the point of maximum moment, which is 24,646 pound-foot is highlighted here. This is a maximum at x equal to 0. Then these are the values of the moment based on the expression. We have here at x equal to 9, we find that the starting the second degree curve. And after this, there will be a straight line from x equal 16, from x equal to 20, and at the right support we have a 0 moment. We have come to an end of our discussion for the practice problem. Thanks a lot. God bless you all, and goodbye.